Okay, so 2.6 in the book, if you're following along, this is analyzing rational functions, right? So really the big things we're going to try to figure out: where are their asymptotes, where are their x-intercepts, what they kind of look like in general, how we can draw these without having to plot 1,000 points, right? How can we just kind of use these structures, the asymptotes and the zeros to help us here? So the first thing we have here is we have this graph. It's on your note sheet here. And we're asked to identify a horizontal asymptote. Right? So if we remember, asymptotes are lines, a lot of ways to describe them, but one way would be that the curve approaches but never quite reaches. Okay? Now, sometimes it will cross them, but there's different cases here, sort of. But if we look horizontally, if we look right through here, does this appear to be the horizontal asymptote? We see that as we go to the right, the curve approaches this line that I'm using the ruler for. As we go to the left, the curve approaches that line. For rational functions, they tend to work on both sides. So for this one, we would say that our horizontal asymptote But we would say that our horizontal asymptote is going to be the line y equals 2. Now, it's really important to put y equals because that tells you that it's a horizontal line. Right? If you just say 2, it could mean lots of things, right? And it kind of means nothing on the coordinate plane. It's not a point, it's not an equation, it's just a number, which, again, is not super clear. So it also asks us then about a vertical asymptote. And just in our warm-up today, we talked about an infinite discontinuity and how that was the same as a vertical asymptote. So that would be our line that's vertical. Funny how vertical asymptote's vertical. But we see right here that the curve approaches this, right, from the left and from the right. Right, as we approach this asymptote from the left, it drops down. As we approach it from the right, it goes up there. So that would be our vertical asymptote, and that would be the line x equals 3. Again, vertical line is x equals, horizontal is y equals. One way to kind of remember which is if it only hits the x-axis, right, it's going to be x equals. If it only hits the y-axis, it's going to be y equals. Maybe if you tend to get those confused. Now, something that's probably you've not done before is we're going to write the behavior. There's two types of behavior we're talking about. We're still talking about end behavior, which means as we go to infinity, right, and we go to negative infinity, we can write that using limits, and we're also going to talk about what's called asymptotic behavior. It just means behavior near the asymptote, right? It sounds like you're, I don't know, that's just a weird phrase, asymptotic behavior. But for this, if we're asked to write the behavior in limit notation, so to write the end behavior, and here you have to watch out. Sometimes people are not very careful with their language here, but the end behavior indicates what happens as you approach the ends of the function. So as x goes to infinity and as x goes to negative infinity. So it's going to be these two limits. We're going to say the limit, didn't give us the name of the function. Oh, we'll just call it f of x. As x approaches infinity, and then the limit of f of x as x approaches negative infinity. This looks just like what we did with polynomials, doesn't it? Same setup. But here, as we go to the right forever, we said there's a horizontal asymptote. The curve is approaching this line y equals 2. So we would say the limit of f of x as x approaches infinity is 2. Now, it might never equal 2. In this case, it most likely never would, but it's going to get so close to 2, it's going to effectively be 2. Does that follow for everybody? Now the other end is as we go to the left forever, as x approaches negative infinity, and notice there's an arrow down here, and this is an equal sign. It's something on the test we could work a little bit on our notation. It was pretty good, but we could do a little better. But that would be 2 also, because as we go to the left, it's also going to approach 2. I would expect with our rational functions, we're going to usually get both ends are going to have the same behavior. There are other functions where one end will have one behavior and one will have a different behavior. But for rationals, we're going to expect to see this. The other type of behavior we want to talk about, as I mentioned this word, is asymptotic behavior. And again, that means as we approach the asymptote. Now, in this case, we said there's a vertical asymptote at x equals 3. But we could see if we approach that from the left, the function has much different behavior than if we approach that from the right. One goes up, one goes down. That's pretty, I don't think it could be any more different, right? So the way we write this is we're going to approach it from both sides. And what we do is if we're going to go from the left, we say the limit of f of x as x approaches 3, because that's where the vertical asymptote is at. The way we indicate that we're coming from the left, this is really important, is we put a negative up there where the exponent would go. So this means as x approaches 3 from the left. So that means on your graph, look a little bit to the left, like at 3, like at 2, and if you approach this vertical asymptote, what does the output value do? It goes down, right, forever. And going down forever we call negative infinity. So we'd say as x approaches 3 from the left, f of x approaches negative infinity. So the other way we write this would be the limit of f of x as x approaches 3 from the right. So we'd still put x approaches 3, but we would put a plus sign there where the exponent would normally be at. And then from that, we see that as we approach 3 from the right, we see the graph goes up forever. So that would either be infinity or positive infinity. You'll see it written both ways. Okay, so again, we have end behavior. It talks about as x goes to infinity and negative infinity. Then we have asymptotic behavior, which is what happens as we approach 3 from the left and 3 from the right. So you could think of this one, you could think about like 2.9 and 2.99 and 2.999. What's going to happen? Right? We're getting closer and closer to 3, but we're a little bit less. Here we're getting 3.1, 3.01, 3.001. We're getting closer and closer to 3, but we're coming from the right. Is that working for everybody? Yeah. All right. Okay, so the next part of our worksheet here, we're just kind of looking at some general pictures and how we can describe here would be this top part would be asymptotic behavior. I didn't put the word there, but it would be asymptotic behavior near the asymptotes. And this would be end behavior because you're talking at the ends of the function. So they're using the same limit notation. They seem very similar. They usually have some infinities flying around, right? Negative infinities, but they are a little different, right? You're talking about as you approach some line, it's kind of in the middle of the function, vertical line versus the ends of the function where you're going to infinity. So for this first one, we see this dashed line here at A, that's our vertical asymptote. We see the curve as we approach the vertical asymptote from the right, it's going up, correct? So we would say as x approaches A from the right, so that'd be A with a plus, where the exponent would go, f of x is approaching infinity, right? Because it's the output's going up to infinity. We good there? Did everybody have that? I hope. So the next one here, right, we're approaching the same, it looks like another vertical asymptote at A, but this time we're approaching from the left, and it looks like the curve goes up. So the limit of f of x as x approaches A from the left would be infinity, is how we would write that one there. The next one, we're looking at the same vertical asymptote, but this time as it approaches from the right, it goes down, right? And down would be the negative infinity direction. So we'd say the limit of f of x as x approaches A from the right is negative infinity. Again, sometimes you will see positive infinity and positive infinity written, but if you just see infinity, it means the same thing as positive infinity. And then over here, we're approaching A from the left. So A from the left, and then f of x equals negative infinity, right? So it tells you what's going on as you approach this vertical asymptote, right? Is it going up? Is it going down? If you have an infinite discontinuity, a vertical asymptote, it's going to do one of the two pieces when we're with the things we do now, right? Things we do Okay, end behavior of horizontal asymptote. So here, obviously, we have a horizontal asymptote. One very significant difference, which as soon as you understand this, is not a big deal, but curves will cross horizontal asymptotes, right? A vertical asymptote is absolute, right? If there's a vertical asymptote, you will have no point that has that x value on your graph. It will never cross it. It will be a discontinuity, right? Horizontal asymptotes just tell you what happens at the end of the function. It doesn't tell you anything about the interior of the function, so you could completely cross over it. It's not a big deal at all. Okay, so like in this case, if you notice the curve, it crosses over it, you might think, hey, we can't do that. Actually, we can. That's not a problem. So in this case, we see that we have this horizontal line here at B, so that would be the equation y equals b. And we would say, and here for end behaviors, we don't really do the plus or minus part, but we'd say the limit of f of x as x approaches b, as we approach b, would be, oh, I'm sorry, that was wrong. It's not approaching b, is it? As we approach infinity, f of x equals b. Kind of missed the equal sign there. So again, for this end behavior, the limit of f of x as x approaches infinity, right? As x goes to the right forever, the curve approaches b. It doesn't appear to be any sort of end behavior on the left-hand side of the function, right? So we wouldn't write a statement there. Doesn't appear to be one. As we look at this next one here, as we go to the left, we see that our curve is approaching this horizontal line. So we'd say that the limit of f of x as x approaches negative infinity is equal to b. Also there. Okay, so on the back of our note sheet, we have this graph here as we look. Sure appears to be a vertical asymptote at x equals 2, doesn't there? And a vertical asymptote at x equals 6, right? Notice the curve does not cross over those. That's what a vertical asymptote is. Looks like a horizontal asymptote here at y equals 1. Appears everything's kind of approaching that, kind of being stable. So we're going to identify all asymptotes and describe the behavior near each asymptote. So our vertical asymptotes, we just said, would be at x equals 2. Again, we're going to write that as an equation. And then at x equals 6. Right, these would be our vertical asymptotes. Now, each of those 2 and 6, you can approach 2 from the left, you can approach 2 from the right, you can approach 6 from the left, you can approach 6 from the right. So just to kind of take a look here, if we say what is the limit as x approaches 2 from the left of f of x, we'll just call it f of x. We didn't really have a name on it. So as we approach 2 is right here, right? This is the vertical asymptote. As we approach from the left, the outputs of the function get bigger, correct? They go up. So this would be infinity. As the limit of f of x as x approaches 2 from the left. So here's 2, we're approaching from the left. We see that it drops down, correct? So again, 2 represents the x value, so when we're writing this limit, we're talking about the y value, correct? So what's the y value do? It drops, so that would be negative infinity. Okay, so take a second. Decide what the limit as x approaches 6 from the left of f of x, and the limit as x approaches 6 from the right of f of x would equal. So again, take a second. So with this one, this is at saying what happens to the output, right? F of x, the output, as we approach 6 from the left. Well, here's 6. As we approach from the left, we see the curve is going down. Right? So we would say negative infinity. And then as we approach 6 from the right, we see that it's going up. So that would be positive infinity. We all get that? Yeah, good. All right, horizontal asymptote. There appears to be 1, correct? And it appears to be actually y equals 1. Now again, up here, this would be the asymptotic behavior, right? Asymptotic behavior. So then here we get the limit is x approaches infinity of f of x, and the limit is x approaches negative infinity of f of x. Right? End behavior, you'll always start with those two pieces, just like we saw with polynomials. There's nothing new there. Same idea. Now the thing that is new is as we approach infinity, we see that it's flattening out and approaching the line y equals 1. So that would be 1, and this would also be 1. That's how that would work there. Questions? We good? All right. Okay, so as we look at this, we have a let R be a rational function R of x. The top is just a polynomial definition, right? A sub n, x to the n. It just decreases powers till you get to a sub 0, the constant term. On the bottom's the same thing, except your coefficients, instead of being a sub n or whatever, it's b sub m. It's just a different case. Here, m being the largest power on bottom, the degree of the denominator, b sub 0 is the constant term, all that good stuff. So just if we're given one of these, how to identify pieces in that rational function, the vertical asymptotes of R are the lines x equals a, where a is, so again, vertical asymptotes, right? We're going to have to look at the denominator, correct? So vertical asymptotes would be a is where the denominator is equal to 0, right? So a is where the denominator is equal to 0. So usually we'll be able to factor the denominator, or it'll just be a linear factor, and you can figure out when it's equal to 0. That's going to be your vertical asymptotes. Yeah? If n equals m, or well, then what we do here to find asymptotes, and you may or may not have discussed this in Algebra 2, probably you did, but in terms of finding the horizontal asymptote, what you're going to want to do is compare the degree of the numerator and the degree of the denominator. Okay. So if n is less than m, that means the numerator has a smaller degree. So maybe the numerator is squared, the denominator is cubed. Maybe the numerator is a constant, and there's an x plus 5 on bottom. Those would be cases where the top degree is smaller. In that case, then R has a horizontal asymptote, and the horizontal asymptote is just the equation y equals 0. Right? So as you go to the ends of the function, if the numerator has a smaller degree, it's just going to approach the x-axis as you go to the ends. Which makes sense, right? You got a bigger degree polynomial on bottom, so the number's going to get bigger, faster than the numerator. Okay, if they have the same degree, so say you have a squared on top and a squared on bottom, in that case you're going to take the ratio of leading coefficients. We'll look at an example, but that would just be, if it's a 5x squared on top is the biggest degree term, and a 2x squared on bottom, the horizontal asymptote would be y equals 5 over 2. Just that ratio of leading coefficients. And then if n is greater than m, so the top has a bigger degree. So remember, the numerator, we would say that is degree n. The denominator is degree m. So if the degree of the numerator is bigger, it's just going to grow forever. It's going to grow a lot faster than the denominator. So there is no horizontal asymptote, but a slant asymptote, which we'll deal with later this week. It's called a slant asymptote. Could be a slant. You could get some other weird behavior, but we'll kind of look at slant asymptotes. And really, guess what? Instead of being horizontal, it's slanted. Like that's, yeah, it's really not a very, they didn't do a good job hiding it by the name. Kind of right there. All right, so these are, once we know our asymptotes, right? We find our verticals by looking at the denominator. We compare the numerator and denominator to find our horizontal. To find the intercepts, to find the x-intercepts, that would be whenever the numerator is equal to 0. So for this, we're going to set the numerator equal to 0. and solve, right? So if the numerator equals 0, that should be an x-intercept. Now, kind of looking ahead, if you have the same number makes the denominator equal to 0 and the numerator equal to 0, that takes us back to our warm-up. That would be a removable discontinuity. Like if it shows up both places, it's a removable discontinuity. But it doesn't happen a lot, but it does happen. And then to find the y-intercept, every function ever, to find the y-intercept, you just replace every x with 0, right? So, but actually what happens here, because it's a rational function, everything becomes 0 except the two constant terms, right? So two ways you could let x equals 0 and simplify, which is for any function, or you could just do, it would just be, or it's just where the constant term divided by the constant term, right? Because everything that has an x on it becomes 0. So it's just the constant divided by the constant. Any questions with that? Does this seem familiar from the past? Yes?
How did you say we solved for the x-intercept?
The x-intercepts, you just set the numerator equal to 0 and you solve. So usually you factor it first, but if you don't need to factor, you just set them equal to 0 and go ahead and solve it there. Is that good? So let's look at some of these here. Okay, so as an example here, we have f of x equals 3x plus 5 over x plus 2. It's rational because we have a polynomial on top divided by a polynomial. That's what a rational function means. And then what we'll do here is we're just going to identify all those pieces. So remember, we know that you find the zeros from the numerator, vertical asymptotes from the denominator. You compare the degrees to find the horizontal asymptote. You put a 0 in for x to find the y-intercept. So we should get, at least 1 point, probably 2 or 3 points, and you should get some vertical asymptotes. That really makes it pretty nice to graph and sketch, and we'll look at that more tomorrow. So with this, to find the x-intercepts, which again, there could be more than one, like a lot of things we've seen. Remember, we just set the numerator equal to 0. So we'll say 3x plus 5 equals 0. Solve it. We get x equals negative 5/3. Now, it's still an x-intercept. If you write this, this looks like a vertical line on the plane. Does that make sense? So when you say the x-intercept, you want to say negative 5/3, 0. Like that would be our x-intercept. Write that as an ordered pair. It's going to save you a lot of difficulty and help you keep things straight. Now the y-intercept, right, because it's a function, there can be at most one of these. Right? You can't have 2 of them or it fails the vertical line test. So here for this one, this is where you let all x equal 0. So you actually find f of 0, which gives you 5 over 2. Right, so that would be the ordered pair, 0, 5/2. So we have a couple points already on our graph. We're asked about the vertical asymptote. Remember, that's where we set the denominator equal to 0 and solve. Now this will be a line. This will be an x equals equation. So the denominator is x plus 2 equals 0. So x equals negative 2. That would be our vertical asymptote. The horizontal asymptote, that would be where we compare the degrees, right? So we look at the degree of the top, the degree of the bottom. They're both first degrees, correct? If they're the same degrees, then it's just the ratio of leading coefficients. So that would be 3 over 1. So that would be the line y equals 3 over 1. Of course, we would actually say that that is equal to y equals 3. Okay, so once we found those points, and next time we're together, we'll look at how to actually use these points to sketch something. But with this, let's see, we have 1, 2, 3, 4, 1, 2, 3, 4. So we have a horizontal asymptote here. When you graph those, you'll want to make those dashed lines. And then we have x equals -2. Right, that'll be a dashed line for a vertical asymptote. We have -5/3 0, which would be about right there. And we have 5/2 0, which would be about right here. So we're starting to get part of the graph, and we'll look at how to get the rest of the graph tomorrow.